Good afternoon, dear students. Today we are going to discuss about isotope tracer technique. Now, the phenomena of natural radioactivity was accidentally discovered by the French scientist Henri Becquerel when he found that the crystals of potassium uranyl sulfate spontaneously emitted a radiation which could blacken a photographic plate. And that is how natural radioactive element was discovered. Subsequently, other naturally radioactive elements like radon or radium, thorium, radon were discovered, okay, by Madame Curie. The discovery of radium has been linked with the legendary Madame Curie. But these natural radioactive elements do not actually find any application in biology. Rather, we develop isotopes. Okay, for use to be used in medicine field, we develop isotopes. Okay. Now, what is an atom? What is an isotope? And what is radioactivity? Let us understand. What is an atom? It is composed of a positively charged nucleus around which there is a field of electrons, or electrons spin around a positively charged nucleus in an atom. Now, the nuclei of the atom is composed of two major components. They are protons, which are positively charged, and neutrons, which are neutral. The number of electrons which are negatively charged in an atom is always equal to the number of proton. That means negatively charged electrons is equal to the number of positively charged proton, and hence an atom is electrically neutral. This number is known as atomic number. Okay. Neutrons are uncharged particles with a mass approximately equal to that of a proton. The sum of protons and neutrons in a nucleus is known as mass number, represented by the letter A. Okay, so what is A? A is equal to Z, that is atomic number, plus N. N denotes the number of neutrons and Z denotes the number of electrons or protons. So A is equal to, that means mass number is equal to atomic number Z plus N, that is number of neutrons. Okay. Now, what is an isotope? The word isotope is derived from the Greek word iso and topos. Iso means same, topos means place. Okay, so isotopes are the, you can say, same atoms having different mass number. Okay. Now, the word isotope is derived from the Greek word iso means same and topos means place, and thus signifies the same position in the periodic table. Okay, they have same position in the periodic table. The scientist Soddy in the year 1913 first established the existence of atoms of the same element with different atomic weight and called them isotopes. Isotopes are atoms of a given element having same number of protons but having different number of neutrons, and hence their atomic mass is different. Okay. The number of stable isotope that element possesses varies widely. For example, calcium has 6 different isotopes. Okay. Carbon has 3 different isotopes. Sodium has only 1, N24, like that. So, what are isotopes of a given are atoms of a given element having identical number of protons but having different number of neutrons. So, having different atomic mass, right? So, that is isotopes. Now, in medicine, in the field of medicine or biology, we use different radioactive isotopes for carrying out variety of studies. When we'll study the applications of isotope, we will study that. Okay. Now, what is radioactivity? In general, the stability of an isotope of a given element is dictated by the ratio of number of protons to neutrons. If number of proton to neutron is equal to 1, means number of neutron is equal to number of proton, the nucleus is very stable, the atom is very stable. Stable isotopes for element having with low atomic number tend to have equal number of protons and neutrons, whereas stability of elements with higher atomic number is usually associated with a neutron to proton ratio in excess of 1, but it should not be 2 excess. It can thus be summarized that neutron to proton ratio of a stable isotope lies within narrow limit, so that an isotope outside this limit is very unstable. Okay, so n to z ratio in lower I mean isotopes having um, lower you can say atomic number have same, the n is to z ratio is 1. That means stable isotopes of elements with low atomic number have equal number of neutron proton, whereas elements having higher atomic number, it may be in excess of 1. Okay, but there is a limit, there is always a narrow limit. But when the ratio of n to z ratio increases beyond the narrow limit, the element becomes the atom or element becomes unstable. Such a nucleus which is unstable tries to maintain or tries to adjust the n to z ratio towards stability. When a nucleus which is unstable wants to become stable, it adjusts the n to z ratio, and when it is adjusting the n is to z ratio, it gives out radiation. This phenomena of emitting radiation is called as radioactive decay. That means it is emitting out radiation. Thus, the phenomena of radioactivity can be seen as an attempt on the part of isotope to achieve stability. Okay. So, any isotope, when it is unstable, it releases radiation, which we call as the process by which, or the phenomena of emitting of radiation is called as radioactive decay. And it can be seen as an attempt on the part of isotope to become stable. So, whenever an isotope wants to become stable, it will emit out radiation. And those radiations are to be measured. Okay, and these sometimes there are two types of isotopes: radioactive isotopes and stable isotopes. Okay, radioactive isotopes are generally measured by using say for example, what we are going to study is Geiger counter and scintillation counter, whereas stable isotopes can be measured by mass spectrometry or nuclear magnetic NMR spectrometry. Okay, now what are the different units of radioactivity? The unit of radioactivity is Curie, represented by Ci. What it is? It is defined as quantity of radioactive material in which the number of disintegrations per second is the same as that of 1 gram of radium. What it is? 3.7 into 10 raised to 10 disintegrations per second. So, what is Curie? Quantity of radioactive material in which number of nuclear disintegration per second is the same as that of 1 gram of radium, that is 3.7 into 10 raised to 10 per second. Now the Curie is a large unit, and hence another unit was introduced called as millicurie. Okay, and only millicurie are needed for tracer application. Curie is a large unit. Actually, the requirement of radioactive isotope in tracer application is generally in a very small amount. So it is represented by millicurie. The Curie refers to number of disintegrations actually occurring in a sample rather than disintegration counted in the radiation counter. Okay. So Curie actually measures the number of disintegration actually taking place in the sample rather than that shown by the counter. Now, there is another unit of radioactivity because Curie is no longer accepted. So, the international unit of radioactivity, that is SI unit, is the term becquerel, BQ, to replace the term Curie, which is currently in use. So, becquerel is the unit of radioactivity which is currently in use. A becquerel is defined as 1 disintegration per second. Becquerel is 1 disintegration per second. So, Curie is therefore equal to 1 Curie is equal to 3.7 into 10 raised to 10 becquerel. Okay, so that is the unit of radioactivity. Now, what is the interaction of radioactivity with matter? Okay, whenever a matter comes across a radioactive isotope or comes across a radiation, what will happen? The interaction of radioactivity with matter can be divided into two broad categories: excitation and ionization, depending upon the strength of interaction. That means whenever a matter, a gas particle, or any particle is struck by a you can say radiation, whenever a matter is struck by a radiation, two phenomena can take place. Number one, excitation, and number two, ionization. The phenomena of ionization is generally measured by using a gas filled chamber like ionization chamber, proportional chamber, or Geiger counter. Excitation radiations are generally measured by scintillation counters, right? So what is excitation? Radiation can interact with the orbital electrons of the intervening matter that it is passing through. Okay, the radiations, when they are passing through a matter, they interact with the orbital electrons of the matter. This interaction may be weak, capable of only lifting electron to a higher energy orbital from its ground state, right? So excitation radiation, when they pass through a matter, what they do, they lift the electron from lower energy level or ground state to higher energy level. This electron which has been transferred to higher energy level eventually wants to come back to its ground state. And when it wants to come back, when it comes back to the ground state, energy is released. The energy difference between the ground state and the higher energy orbital is emitted out as electromagnetic radiation. This is to be counted, and this is counted by using a scintillation counter. This type of interaction is known as excitation. So what excitation radiation do? They excite the electrons from ground state to higher energy orbital. When the electron comes back to its ground state, it emits out electromagnetic radiation equal to the energy difference between ground state and higher energy orbital. This type of interaction is called as excitation. What is ionization? Now here there is a closer interaction of radiation with matter. Okay, so the close interaction of radiation with matter imparts so much energy to the matter that the orbital electron leaves the atom completely. Okay, the orbital electron do not get transferred to higher energy level. Rather, they leave the atom completely. This results in the formation of ion pair, like positively charged ion or negatively charged electron, right? This results in the formation of ion pair, a positive atom and a negative electron. This process is called as ionization, right? Ionizing radiations or ionizations are generally measured by using a glass filled tubes. Okay? So how to measure the radioactivity? Measurement of radioactivity. Radiations react with matter to cause ionization and excitation. Both these type of interaction with matter are utilized in measuring radioactivity. The simplest arrangement to measure radioactivity involves measurement of ionization, that is caused by radiation in a gas filled chamber. So gas filled chambers like ionization chambers, proportional counters, Geiger counters are used. Scintillation counters, on the other hand, exploit excitation caused by radioactive interaction in order to measure radioactivity. So scintillation counters are used for measuring excitation radiations, whereas you can say gas filled chambers are used to measure ionization radiations. Now, this graph here we are going to discuss about ionization, measuring alpha, beta, gamma, whatever radiations. So this graph shows you the relationship between the voltage applied and the number of ions collected or current that is generated. And the regions are also mentioned here. See, generally whenever a radiation strikes a matter, okay, when a radiation strikes a matter, the energy of the radiation is absorbed by the matter, and as I told you, we are here actually studying methods based upon gas ionization of gases, right? Alpha, beta, gamma radiation have different capabilities of ionization. So first we are going to discuss about ionization chambers, then proportional chamber, then Geiger counter, right? Whenever, see, you can see from this graph the applied voltage and the charge collected or the current that is generated. Initially, when current is applied, what happens? The energy is absorbed and the matter, the atom undergoes, the isotope undergoes ionization to form negatively charged electron and positively charged ions. These, you can say, oppositely charged particles move towards electrodes, right? Initially, the two can attract each other and they can reunite. So, to prevent the reunion of positive and negative ions that are generated, a strong electric field is created which accelerates the particles towards oppositely charged electrode. Okay, that is what happens in the ionization chamber region. The first here you can see ionization chamber region, where in this region operate the ionization chambers. Okay, ionization chambers are not used in biochemistry now today, but we need to understand this before we study the Geiger-Müller counter. Okay, then if the current is further increased, see, initially you can see a prolonged can say effect. There is a plateau when the current obtained is plotted against the applied voltage. A region of saturation current shows a long plateau. Okay, there is a long plateau. You can see this is a long plateau. Okay, this is the region where ionization chamber works, right? When you further increase the current, what happens? When you further increase the current, right? There is a rapid increase in current. When you further increase the applied voltage, there is a rapid increase. There is a rapid increase in current is observed. What happens here? Ionization by collision is responsible for this. Okay, here there occurs ionization of the you can say matter or gas, whatever, the gas filled chambers. So ionization of gas particle occurs because of collision. So you can see a steep increase in the current. This region where there is a steep increase in current is called as proportional counter region. Okay, proportional region in which operate the proportional counters. So proportional counters measure the radiation in proportional region. Ionization counters measure the radiation in ionization region. Okay, then proportional region where operate the proportional counter, and then comes the Geiger region where operates the Geiger-Müller counter that we are going to study in detail. Is that clear? So here what happens when you apply electric field, there is rapid increase in current due to you can say there is increase in current because of ionization of the matter, you can say matter, molecules of the gas. Then there is a steep increase. Why? Because further ionization by collision of primary ion occurs. See, initially electrons generated in the ionization chamber migrate to electrode, but in between, they intervene or struck different neutral atoms or neutral molecules of the gas. When they strike the neutral atoms or molecules of a gas, collision occurs. They lose their kinetic energy, but because you are applying electrical energy, they get energized due to the applied electric field, and the process is repeated several times. So primary ions gives rise to secondary ions, and they gives rise to tertiary ions. This type of gas ionization amplification is called as Townsend avalanche effect after its discoverer. The current that flows increases is directly proportional to the primary electrons produced. So in the proportional region, we can see a sharp increase in the current. Okay. Now, beyond this proportional counter region, when the voltage is still applied, okay, beyond the proportional region, when you still apply voltage, then the proportional region is left behind and the size of the pulp ceases to be proportional to the number of primary electron or the voltage applied. The discharge that is produced here by each ray does indeed increase as the voltage rises, but the relative increase is very small. Okay, finally we reach a stage where the size of the pulse is totally independent of the primary ionization. All discharge produced by any type of radiation are nearly equal in magnitude. This region is called as Geiger region, in which operate the Geiger-Müller counter. What happens in Geiger region? All discharge produced by any type of radiation are nearly equal in magnitude. Okay, because the size of the pulse is totally independent of amount of primary ionization. This region is called as Geiger region, where Geiger-Müller counter actually operates. So there is initial ionization region, then there is proportional region where there is sharp increase in the current according to the voltage applied because of collision of molecules, ionization because of collision of molecules. Okay, so primary electrons give rise to secondary and tertiary and so on. Okay, and then comes the Geiger region where Geiger-Müller counter operates, right? So in order to understand the Geiger-Müller counter, we need to understand this graph of what? Graph of current generated against voltage applied. Okay, so GM counter operates beyond the region where ionization chamber and proportional chambers work. As electric field increases across the chamber, there is rapid increase in current, due to which further ionization by collision of primary ion occur. The electrons that are generated in ionization chamber will migrate towards oppositely charged electrode. Meanwhile, they intervene or strike different neutral atoms or molecules, and due to this collision they lose their kinetic energy, but they again get energized due to the applied electric field, and the process gets repeated several times. So primary ions gives rise to secondary, and secondary ions give rise to tertiary ions, and so on. This process is repeated many times in a Geiger-Müller counter. Okay, and this type of gas ionization amplification is called as Townsend avalanche effect, after the name of its discoverer. The current flow increases, which is directly proportional to primary electrons produced. This happens in proportional region. The basic advantages, and then comes the Geiger region where the Geiger counter operates. Okay, the basic advantage of Geiger counter is derived from the amplification. Initially, amplification has occurred. Each primary ion pair yields close to 100 million secondary ion pairs. The amplification is so great that extremely simple external electronic amplifier is sufficient. Okay, initial amplification is so great that how much of amplification? Each primary ion pair yields close to 100 million secondary ion pairs. So much of amplification is taking place. So we need a simple amplifier which is sufficient. This simplicity imparts stability to the Geiger counters. By using Geiger counters, we can use, or different isotopes can be measured, right? As a precautionary measure, a stable high voltage is applied. Any change in voltage results in large changes in amplification. So a stable high voltage, but a stable high voltage is required. If you look at the construction of a Geiger-Müller counter, okay, what is Geiger-Müller counter? It is a device which is used for detection and measurement of all type of radiations, alpha, beta, gamma, but it is not so efficient in measurement of gamma radiations. Okay, basically it consists of a pair of electrode, positive negative charged electrode, which is surrounded by a gas. The electrodes, across the electrode a high voltage is applied. The gas that is used is a, you can say, inert gas like helium or argon. When a radiation enters the tube, it ionizes the gas particles. Okay, when it ionizes the gas particles, electrons are generated. They are attracted towards opposite electrode, and hence electric current is produced. This current causes a pulse. Okay, and it is counted. Okay, the pulse is counted by the scaler. Right, now let us see. The apparatus consists of two parts. There is a tube and another part is counter plus power supply. Two parts, one part first is the tube and the second part includes counter and power supply. The Geiger-Müller tube is usually cylindrical, having a wire down the center. The counter and power supply have high voltage control and timer option. High voltage is established across the cylinder and the wire. Cylinder is serving as one electrode and wire is serving as another electrode. Whenever ionizing radiation like alpha, beta, gamma particle enter the tube, it ionizes some of the gas molecule in the tube. From these ionized atoms, electrons are knocked out of the atom and the remaining atom is positively charged. So the positively charged atom will move towards the negative electrode and the electron will move towards the positive electrode. The electrons that are knocked out from the atom are attracted to the positive electrode and positively charged are attracted towards the negative electrode. This produces a pulse of a current. This produces a current in the wire connecting the electrode, and this pulse is counted. After the pulse is counted, the charged ions become neutralized and the Geiger counter is ready to record another pulse. Okay, for proper use of Geiger counters or Geiger-Müller counters, you have to maintain appropriate high voltage across the electrodes. If the voltage drops down, ionization will not take place, and if the voltage increases too much, it can damage the instrument or the gas tube. Okay, now let us see how the instrument looks like. 1 minute. Okay, so this is a Geiger tube of Geiger-Müller counter. Okay, the tube is of rugged metal case which usually serves as cathode. As you can see here, this is a tube. Okay, Geiger tube made of rugged metal or acts as cathode. In the center there is a tungsten wire which acts as anode. Okay, so this is the anode. Now there is a mica window. Through the mica window comes inside the, what comes inside through the mica window? A radiation. Okay, so radiation comes inside, right? The radiation goes and strikes the gas particles, gas molecules. What is the gas? The gas is generally a you can say neutral gas like argon or helium. So what is written here? 90% argon and 10% ethyl alcohol vapors. So the gas, the chamber is filled with gas, that is argon, right? So whenever radiation strikes the gas molecule become they get ionized. Positive and negative ions are formed. Electrons move towards positively charged electrode, that is anode, and so on, and the current, the circuit is completed, current is generated, the current is then measured. Okay, a simple amplifier is required and there is a digital counter which counts the pulse or the current that is generated. This is the simple construction and working of a Geiger-Müller counter or a Geiger tube. And the next class we will discuss about the disadvantages and advantages of using a GM counter.